Thank you very much for the nice introduction, and thank you also for inviting me and giving me the opportunity to speak to you today. Good morning from Germany. I think we had a great start with the first speaker today. I saw many elements that you will find relations to in my presentation, um, in which I want to give you a glimpse into what digital transformation of the quality structure is all about, where NQI could relate to, what NQI could start doing, and I will focus on various things that are possible, and we focus on the machine actionable information, a bit on AI, and on the Internet of Things. Of course, the topic of digital broad, and it may seem overwhelming when you start looking into what topics you may want to consider in the journey of digital transformation. So I will try to give you also some kind of an orientation where one could start with the digitalization and then following the digital transformation. The presentation is structured basically in two parts, where in part one, I would like to try and give you an idea of what potential answers could be to what is this digital transformation all about. That, of course, from the perspective of the quality infrastructure with a focus on metrology. What does it mean for a quality infrastructure? What does it mean for metrology institutes, for standardization, accreditation, and so on? And why should I care? So why should I take efforts to take part in the digitalization of the international quality infrastructure systems? In the second part, then, I would like to give some ideas of how one could get started with this digital transformation. Of course, we all started with digitization, so we all are working digital just right now, right? So it's not that we are at the very beginning, but to the digitalization and digital transformation journey, and I want to give you some examples of how others have started this journey, and maybe you can take some away from this as well for you. In the digital world, digital era, everything is about information. And today, when you look into how information about a product is provided, you typically have a small amount of information given directly at the product. Maybe there's some marking on the product. Maybe there is an icon or a badge or whatever, for which people that know what it means then know whether they can have some trust in the quality of that product. In the digital era, this will very likely be replaced by digital information. For instance, very simple, there could be a QR code, and the user, but also maybe the verification officer, the metrologist, whoever wants to have more information, can go there with a smartphone or another camera, scan that QR code, get to a website or platform or other online available source to receive more information. So it's an immense increase of the amount of information you can provide. But that's not needed. What you need is you need to have exactly the information for the decision you need to make. And I have an example here on the left-hand side from what you all know, a train station or an airport. There you have these dashboards, and they show you, is my flight on time? To which gate do I have to go to catch my flight and to board it? If it is delayed, how much it is delayed? Is it cancelled or not? So very, very basic information, but exactly the information you need at that point in time. you don't need to know at that point in time maybe what the concrete status of the airplane is. If it is delayed, you may be interested why, but you don't need it to make a decision right now, and so on. So you have a very condensed amount of information to provide you with everything you need to make a decision at that point in time. Of course, to generate such a dashboard, you need to have interfaces between different platforms, between different systems, because in the end, all this information that you see in this one place is coming from different sources. And that also holds true for the what sometimes is called a digital product passport. So when we again go back to the product and you have some way of providing information about the product in a digital way, then um, also this information is coming from different sources. It may be that the manufacturer of the product provides you with that information, but the manufacturer is, of course, not the one that generated the certificates or that generated the information about some of the lifetime information from the product and so on. So again, many different information sources coming together. And if you want to have a similarly condensed amount of information with still the right information to make a decision or to know what you need to know about the product, does it have the right quality? Is it safe to be used in this environment? Or in a measurement situation, is the product still calibrated? Or in another situation, is the product compliant with regulation in place? In order to achieve this, you need to be able to connect different platforms or to connect different information pieces. And in order to do this, you need so-called machine-readable metadata. So if you want to combine information from different sources, you need to have some meta information, some information that describes what do I see here. So for instance, the dashboard on the airport, there is a headline for you as a human to understand, okay, this in this column here, that's the gate information. And this in that column here, that's the departure time of the plane. And a similar way, you need metadata for product information from different digital sources. And when you want to do the combination of the information in an automated way, so that you have a software that extracts and receives the information from different sources and combines them in a proper way, then you have to have this in a machine readable way in order to make the software understand. Of course, you need to have trust and confidence in the data that you see there, in the information. On the airport, if the information that your flight is cancelled was wrong, then you may be angry because you took a decision that was based on the wrong information, but it may not be that critical. In a safety relevant environment or other critical areas where you need to have trust and confidence in product information, the manipulation of data and metadata may be much more severe. So you need to protect the information against manipulation in order to have trust and confidence in it, and in order to make actual trustworthy decisions based on that. And there are so many products out there, and there are so many different ways and sources of information to be provided for a product that you want to have a high level of automation. You don't want to have humans sitting there putting together information from the different sources every time and again and update the information manually. You want to have this in an automated way. Software can do this, provided the information is given in a proper way. The where you provide the information can also be automated. Again, the example of a simple QR code. If you scan that and you're led to a dashboard or website or some other source that is showing you the information about the product, then this information can be put together in an automated way and provide you with everything you need to know. So it's all about the information. And in a quality infrastructure, the information about a product has so many important meanings. And it's not just the quality infrastructure, it's everything that is also surrounded. It starts with the development in the company, where you have a team of product designers that want to design a new product. Now, if it's a product that is to be put on a market where there is regulation in place, then these designers would like to take into account the requirements from regulation already in the design phase. Of course, you don't want to design a product and then afterwards change everything to make it meet the regulations. And there is software out there that you can use to write a set of requirements and then let you help you with the software to guide you in the design process. Can be something like, okay, the distance between these two elements must not be smaller than this value, or if you want to have two electrical wires, you have to have an insulation of this type in between them, things like that. Now, when you want to have this in a digital way or be documented in a digital way, then you need to have the information about the design of the product, but also the underlying regulations that you took into account, also documented in that for later understanding. Then you have the meaning of the product, again, information that is later relevant to decide about the quality. Already today, you have this data from the manufacturing that is used when there is a withdrawal from the market because maybe there was an error identified, or some security risk identified or safety risk identified. Then you need to have information about the manufacturing in place as well. Then a product is put on the market, you distribute it across the country or the world. And again, you have additional information. Where is the product put in place? Maybe as to the information, you want to know where exactly it is located. There are more and more examples where companies offer solutions to where they gather the data about the product and then offer services based on the data, like for maintenance of the machinery, for instance. Again, more data in place. Also about the operation, there's digital data that is gathered and used to control the operation, maybe to decide on repair cycles and so on. And then at one point in time, there is a recycling needed of the product. It is at the end of its lifetime and to be recycled in a proper way, again, with documented information about where and how it was recycled. Now, you see that in parallel to the physical lifetime of the product, you also have a digital lifetime of the product. Now, in the recycling, you may need information about the development because you may want to know how to disassemble the product in order to have a more efficient recycling. Or you may want to have information about the resources that were used to design and to manufacture the product. Like what kind of components do I have in that product right here? Also, the operation conditions may be important for recycling. And the other way around, for development of an update of the product or of a completely new product, you also want to have information about the operation. And similarly, you have many use cases where you want to share information between the different stages of the lifetime of the product. So you would like to have a shared digital lifetime of the product. And this is of even more important relevance for the quality infrastructure. Also there, the product has certain connections depending on the stage of its lifetime. Let's assume we have a product in the area of measurement, for instance, a weighing instrument to be used in the regulated area, maybe to weigh for weighing in motion of trucks or for weighing of products on a market, on a supermarket. Then it starts with the conformity assessment. So there is metrology in place, then there is accreditation for the laboratory that performs the conformity assessment in place. Maybe there's also some kind of calibration, for instance, for the measuring instruments used for the conformity assessment. And later, when the product is on the market, there is market surveillance to do re-verification in given intervals. So throughout the lifetime of the product, there is a connection to the quality infrastructure, as you very well know. Now, if we look at this from the perspective of digitalization, then you see that there are many opportunities to improve the efficiency of the quality infrastructure by introducing end-to-end digital processes. Each of the bodies of the quality infrastructure has a certain amount of information. The Metrology Institute has information about the measurement standards, about the measurements that were taken for the product, for the instrument. The conformity assessment body, of course, has information how the certificate of conformity was created, what is for this, what were the analysis and measurements that were carried out in order to decide the conformity. Also, the information about the accreditation of that conformity assessment lab. The accreditation body has information about that body, and later on, the market surveillance also has information. The market surveillance, to stay with them, they need information from conformity assessment, like when they approach a product for a re-verification, they of course need to know, is this product at all conform with national regulation? So they need information that was earlier provided by a conformity assessment lab or body. So when we talk about digital ways to provide the information and digital processes to share information, then it shows that between these different elements of the quality infrastructure, we need to have harmonized interfaces and data structures so that the market surveillance systems can very efficiently work with the data coming from conformity assessment, have trust in the information that they received from accreditation and so on. So in other words, arrows that you see here between the different bodies, these need to be translated into digital processes. And in order to do so, you need to be able to combine the data sources from the different elements to become interoperable and to be able to exchange and share information with each other. One concrete example is a fuel station. It's just one of many examples, but it's one where you see basically all of the QI elements in place. It starts with the product design. So there's a manufacturer. That manufacturer uses as basis for the design of a product an OML recommendation. In this case here, recommendation 139, and takes the requirements given in that recommendation to design a product that is then ready to be put on the market. Of course, they also take national or regional requirements into account, depending on where they want to sell the product later on. Then there is some testing going on based on further standards and regulations like temperature tasks needed to put it in place. So measurements are carried out. In addition to the measurements, there are also other ways to do the conformity assessment, like also containing the safety and the way the measurement values are shown to the customers, and the data security is put in place, and so on. And then when it's placed on the market, you have a declaration of conformity, you have a serial number, and also you have a verification seal put somewhere on the product that a customer can very quickly and see that this product is trustworthy, and you have kind of confidence in the, in this case, measured values of the fuel that you are putting into your vehicle. Now, if we again look at this from the perspective of digitalization, you see that in each of these steps, many things are possible, provided that the information that is needed for that step are given in a proper way. I already had the example of the software guided design of a product. So if the OML recommendation would be available in a machine readable way, such that a product design software could take that into account to extract the requirements needed for that specific product, to highlight what things need to be changed, and in this way guide the product design, it would be much more efficient. The test reports, if that data is available in an automated way. Maybe you have certain test runs, you gather the data and then put this data into the test report that is then needed for by the conformity assessment to then be included there. If this information is given in a proper way, then you can have more insights into the actual properties of the product that may also help the conformity assessment body to decide on the quality of the product. And last but not least, the verification seal. If it's not only a seal like in this very small picture here on the bottom right hand side, but it is, for instance, a QR code, then this can guide the customer, the consumer to a website where not only you see the information that it has a valid verification, it has a valid declaration of conformity, but also can see more information to understand how the product works. And you can also, because in the previous presentation was the task of building awareness of what is quality infrastructure and why is quality important. You can also find ways to structure and visualize this information in a much more understandable and approachable way than you can today with a small marking that you put somewhere on the product. So you can provide the information in a way such that the consumer actually understands and appreciates the working and the outcome of all the things that were taken place by the quality infrastructure. And it could, by the way, also be a way to provide feedback. So if you go there and you see the information coming from quality infrastructure bodies and other sources, you could as well use this as a way to gather feedback. Like, did you have a problem device? Is there something broken? Do you have a question about it, and so on? So you can use that to approach and communicate with the consumer directly via the product using such digital systems. Now, I talked about so many examples why the different sources of information from the quality infrastructure need to come together. And I hope it became clear that we can only achieve that by collaborating, the collaboration between the different bodies of the quality infrastructure. And luckily, this is already started on an international level. Last year, there was the first mentioning and first publication of the so-called Joint Statement of Intent. It is an initiative driven by the CIPM, coming from their work and discussion on an SI digital framework, so what you may call digital traceability. And what they realized very early on at CIPM is that this can only be successful when they do this in collaboration with other bodies of the international scientific and quality infrastructure. So they approached a couple of them as early collaborators and put with them together this joint statement of intent. This text here is just one small part of it, but it contains the essence of it, and that is that the organizations that sign the joint statement of intent commit themselves to collaborate in the digital transformation of the international scientific and quality infrastructure. And looking here on the left-hand side of the slide, you see the organizations that already have signed that joint statement of intent, that already meet regularly to discuss and exchange information, and that over the course of this year will work on creating kind of a hub to increase the collaboration between them towards a wider digital transformation of the international scientific and quality infrastructure. And last year, the General Conference on Weights and Measure, the CGPM, decided on a resolution toward the role of the CIPM in the implementation of the joint statement of intent and also in the further development. And they invite all stakeholders, all organizations, that regional or international, that are interested in digital transformation to collaborate with the CIPM on the SI digital framework, because they want to make sure that whatever is being developed at CIPM and provided by BIPM meets the needs of all stakeholders. Now, to understand what developments are needed in order to come to the situation where you have a trustworthy place where information from different sources of the quality infrastructure can come together, where different systems can communicate and exchange and share information, you need to have kind of a roadmap, right? So where are we today, and how and what are the steps in which we can approach this? As I said earlier, if you want to have a high level of automation for such digital systems that combine information from different sources, you need to have machine readable data. And I will now go a bit more into detail what that actually means and what the steps are to go there to achieve this. And I'm using a model that was created by the standardization community. Here's one particular example from a German national standardization group, or from a white paper from about 2 years ago. And they introduced basically 4 levels of digital maturity or machine readability. Of course, it is written with the perspective of standardization. So it's talking about how a standard becomes machine readable, but you can translate this very easily to all other areas of the quality infrastructure by replacing the document with the standard document with any other document or information needed in the quality infrastructure. And the first step that we in many places already have undertaken is a digitization. So going from paper-based processes to digital documents. In standards, today it's not uncommon. I think it's more or less the most common way you use is you go on a website and buy a PDF document. Also for certificates, today it's not uncommon, in some areas already expected, that you provide the certificate to your customer as a PDF document. There are situations where the customer requests a paper document, but basically that's not needed. And even if it is a paper document at some place in your infrastructure, it already was a digital document and you just printed it out to send it to the customer. The processes behind that, though, that still need to be digitally transformed, digitized, right? So even if you have a PDF document in the end and send it to the customer, the process how that was created, but also the process how that is used, need to be translated, need to be transformed, and that is digitalization. And here's just one example of how we are looking at it with our PTB infrastructures. Of course, that may look differently in other areas, but it's always the same story on a broader level, and that is you offer a certain service, and that service is coming from somewhere, from your customer. For instance, via a customer portal that you offer. You receive that information, and with the order, you receive some metadata. In a non-ideal case, you receive all of this as an email. That is a non-ideal situation because then the information is not structured. You may receive a set of documents as a documentation, and you will then receive some text describing for you as a human to understand what the request from the customer is, but that's it. You cannot provide this information easily to a software that needs to work with that information. That means in that case, you have to go there and type everything in the next system that you need for the next step of processing that order. So ideally, the placement of the order is done in a way that you already have the metadata from the customer in a structured way that you can hand it over directly and automatically to the next system, in our case, a document management system. Then you perform the examinations, being it a conformity assessment, calibration, testing, whatever. And there you also may need information that was provided by the customer, like what is the type of the product, what are the measurement ranges that the customer would like to have a calibration or conformity assessment for, and so on. So if you have in the laboratory automated systems in place, you again want to avoid that somebody has to manually copy information from the document management system to the laboratory system. So again, the aim is to have this in an automated way that the information can be handed over basically automatically. And then you create the certificate. So you have some software in place that creates a document that can be a structured document already. But even if you have a Word document, Word offers the possibility to define data fields and give those fields names, and it provides interfaces to write a software that can fill in these data fields with information from another source. So even there, you could have a kind of a software that takes the information from the laboratory to put it in the certificate. Then again, you also have an invoice where you also need information that was provided by the customer. And in the end, you pack everything together to provide it, for instance, via the customer portal back to the customer. So you see, even in this first step, going from paper to digital, there are so many opportunities to increase the efficiency and to make sure that you're ready for the further steps of the digital transformation. And one way of approaching this digitalization of the next step, that also translates then to what I just described earlier for your internal processes, is to look into the structure of the document. So if you have the PDF document certificate, again, as an example, and provide it to your customer, that's human readable, right? So that person can have a look at it and can understand, and an auditor or a customer or whatever stakeholder could have a look at it and understand as a human what is written there. And then maybe they place it in some folder on some server and never look at it again. Or in many cases, they need information from that to be provided in some system. Maybe they have a quality management system in place where they have to put in the information. Okay, there was a verification or a type approval for that product. What was the date? What is the ID or the number of the certificate, and maybe other information provided in that certificate. Now, if that certificate is only a PDF document, you need a human to type that information into the quality management system. If, however, that document was in a machine-readable document, so a structured document format, you can once write a software that takes the required information from the certificate and automatically integrates it into the system. You may also use that same approach to work with the data and information from that document. And to again, a small step back to what I said earlier, when you have this way of working with structured data, you can very easily combine the different systems to exchange and share information with one another. What does a structured document format mean? Well, we all work with structured documents or with structured data every day. You very likely did it already today. Namely, whenever you open a website, you work with the structured data. In the background of the website, there is HTML, CSS, JavaScript, and many other technologies in place. And what they create is a structured document. And your web browser that shows you the human readable outcome of that takes the structured information to do something with it, takes the structured information of, by the way, here's an image and here are the properties of this image, to then render this information in the way as thought of and desired by the designer and creator of the website. And similarly, whenever you use a web form, you again have structured information that is then later being sent to some server to process that data. So this is structured information, structured documents. And it's always the same idea behind that. You want to be able to write a software that can take the different blocks of information to do something with it. In case of a website, you just want to be able to ensure that the software part of the browser that works with the images knows how to process the image, knows there is an image, this is what you need to do. So you once write the software for the browser to work with every kind of website that contains an image in the structured data format, provided it adheres to some standards, of course. For a calibration certificate, an example is given here. And that could be that you somewhere in the document you have elements that are titled measurement results. And then you can go and define how is such a block structured, a measurement result block structured. How does it look like, what to expect there? And with this information that there is a block measurement results, you can write or let somebody write a software to find the block of information that is called measurement result, extract the information and do something with it. Of course, there's still, when you are at this stage, a lot of manual work to be done because you need to identify the structure of the data in that measurement result. So is it a table? Is it something else? Is it maybe an image? But at least you're able to find that piece of information and send it to some other system. One example from metrology where we have this kind of structured information is the BIPM vocabulary in metrology, the VIM from the JCGM Working Group 2. And if you would directly one-to-one translate this into an XML document, so a structured data format very similar to HTML, so the basis for websites, then you would be able to write a software to automatically extract the definition by saying, give me the definition of quantity. And then it extracts the piece of information, the text block, and provides you with that text block. Similarly, for the KCDB, the key comparison database, and the measurement capabilities entries in the CMC data there, you can have a software using the programming interface of that to extract information. In a certificate, you may use this in two ways. You may provide a direct link of this calibration certificate from the NMI is linked to exactly this CMC entry that the laboratory has, and then a software can take that link to extract the information from the database to compare it to the calibration certificate, or to make use of this in further documentation or management systems. Coming again back to the this dashboard, or what is sometimes called a digital product passport. There you can also have different information sources in a machine readable way on this level 2, so as a structured information. Earlier, I mentioned that one idea of such a digital product passport, so it kind of a dashboard with all the information of the product, it could be that you have some kind of a QR code on the product that leads you to a website. This QR code on the product, by the way, there is already an international standard in place for a so-called digital nameplate. How to structure this, how to structure the URL so that it is a persistent identifier, so that it is available for a longer time and doesn't disappear after several months or so. So that's already in place. Now, when you go to the website, in the background, again, you have structured information. There may be a part of that information website coming from standardization. So what are the standards that are in place? What are the certificates and conformity statements that are in place? What are information coming here by a German association body? You could use the so-called asset administration shell, which is an interface, coming from the area of Industry 4.0. But again, the basic part here is that you have structured information that is then used to create something human readable and do this in a machine readable way to have a high level of automation. You can also have the machine readable information about the sheer existence of a quality statement. Like here's one example from a European company working on a blockchain-based system, but basically they say, okay, they don't want to share the documents, or they propose not to share the documents on a publicly available basis, but share the proof that a document exists. And that can take place, like in this small example here, you have a laboratory that carries out a conformity assessment or calibration. And in doing so, and in finishing that, they send the certificate to the customer, but they also send a digital fingerprint of that document. So that shows you, provides you with an identification of that document without showing you the actual information of that, providing the digital fingerprint to a blockchain system. So that later on, anybody who wants to check, is that certificate that I have here in front of me on my system, is that really valid? Can go there, take the fingerprint of the document, look it up in the blockchain to see whether it is actually true. And in the same way, this laboratory that issued the certificate can also have an accreditation. from an accreditation body or in any other way. And that accreditation body could have provided the accreditation proof, again with a digital fingerprint to that same blockchain, and that could be linked to the digital proof of the certificate issued by the accredited lab. So these informations can be combined. So then you could have again, something like a dashboard or digital product passport that extracts the live information from the blockchain for that product to tell you only what you need to know at this point in time, namely, there is a valid calibration and it was carried out by an accredited calibration lab. That's all you need to know at this place and at this time. If you need more information, you could contact the holder of certificate or approach their databases if you have access to those. Now, again, if you have information in a machine-readable way, you are able to do a high level of automation. And this is one example from an actual metrology set up in place by our colleagues in the United Kingdom, where they have an optical measurement that combines different measuring instruments, like typically the case, and they use digital calibration information from a certificate to have a software in place that automatically adjusts the information, the calibration parameters, the uncertainties. Whenever there's a new calibration, they only provide the certificate to that software, and all the analysis and adoption of the calculations and documentations are undertaken automatically, because the information is provided in a structured format and such as a machine readable document. If you want to go further and even have software be able to work with the actual content, so not only finding in a certificate where is the block with the measurement results, but also work with, for instance, a unit and the value given there, you need to go more deeper into the structure. So you have to have a finer granularity of the structure. And here's one example how you could do this. You could have a structure defined. I have a label that gives me the name of the quantity being measured. I have the value and I have the unit, and all of this in a machine readable way. So we have sub-elements defining this. Again, this increases the level of possible automation and of integration and combination of different data sources. One example how this could be done was developed a few years ago in a European project, and this is so-called DSI. It basically defines a set of required and optional information and how to structure them in order to write meaningful software to work with that information. So it's, if you like, it's the point of view of a software developer on the international system of units. And then you realize that, well, basically the system that we have in place can be very easily and unambiguously understood by a machine if you implement it in a proper way. And of course, there are many other realizations. So it's not just this one developed in that European project, but there are so many more already out there and in use in different communities that all have a certain implementation of how to represent units of measurement in a digital infrastructure. And if, about 3 years ago, the CIPM created an expert group and a task group on the earlier mentioned SI digital framework to address how this can be dealt with. Because if you look at it more broadly, then realize with these many systems in place, and it's over 100 systems worldwide, many systems in place, how to represent units of measurement in digital era, it's again like in the Middle Ages, where each country had its own way of describing measurements, its own system of units. So in order to overcome this, the BIPM developed a an SI digital reference point that can be understood as a digital SI brochure, if you like. So it's a reference point that all the other digital unit representations can be linked to in this way allow the interoperability of the different unit representation systems. And furthermore, this is a basis for services and applications in not only metrology, but again in the wider quality infrastructure to have interoperability between different systems based on measurements. So with the digital unit representation system, the SI reference point, you can refer different services to the same core, to the same reference point, thereby make them interoperable. The BIPM will continue further developing their products like the KCDB with the CMC entries, but also the mise en pratique for the realization of the units, and in this way make them available to be used in digital infrastructures, to develop digital services, and then to develop applications like a digital calibration certificate or digital certificate of conformity. If you want to proceed from this so that you have a very well structured document in such a way that you can build a software to find the information that you need in the document to then do something with it, if you want to increase the level of automation, you need to understand the context of the data. You need to be able to have a software understanding what is it that I see here? What kind of measurement is this that we are working with? So you need to translate the human readable text content in something that a machine can work with, meaning a software engineer can write a software to extract and work with that data. And that is then leading to actual digital transformation. And here's one example of what that could mean. Again, the example of a calibration certificate. There you could say that, okay, and not only do I have a reference to the structural element, namely the quantity being measured, but also I have a so-called, in this case, so-called taxonomy that is standardized somewhere that defines what type of quantity is this. In this case here, measurement of a radius of something. This is important because if you want to relate the information from that information block to another information, maybe to decide whether this can be integrated in your database or where to integrate it, or you want to use it in the automation of a measurement structure, then you need to understand what kind of quantity is this, and then such a taxonomy can help. Again, if we take all of this and look again on this picture of how a quality infrastructure looks like, I think it's clear that we need to start from that level one, the digital documents, and see how we can translate those into structured digital documents to make sure that these different errors between the block elements here can be digitized and that the information from the different bodies can be used efficiently. Of course, you can always have a human take information from a PDF document and type it in another system, but that will not lead to a more efficient quality infrastructure. One example of how that can look like is one that we are looking at in a national project. The project name is QI Digital. It's an initiative where the national bodies of the quality infrastructure collaborate closely to work on concrete use cases that interconnect different elements of the quality infrastructure and their digital counterparts to demonstrate and assess how the quality infrastructure can become more efficient based on digital technologies. And here in this example, you have a conformity assessment body that has a certificate database with which it shares information and exchanges information. there is a need to have an accreditation maybe for that lab. So you want to have a digital symbol of accreditation that you can use then in the reports that you provide to the customer. You, of course, base the assessment on standards. If you have machine readable standards, you can do this in an automated way. And then at the end, if you issue the certificate, you have a digital representation in place where this information is fed into as a digital marking of conformity. And again, here, one example to do this is to use this fingerprint that is then provided in a blockchain or another database. So there are many ways to do this. Of course, the way that is more suitable for your use case needs to be identified based on the requirements you have in the use case. Before I finish the first part, I want to go a bit away from all this machine readability of documents and information to a more broader view of how digital measurement infrastructures will look in the future and what to expect in the digital era. And these are basically three things. Digital communication of data and information will become the standard in all services, not only metrology, but in all quality infrastructure services. I think that's clear. Particular for measurement, the distributed measuring systems and sensor networks will become more important than individual sensors. Examples are smart cities, autonomous vehicles, smart manufacturing, and so on. They all are based on sensor and in a sensor network, the combination and fusion of the data is what really is important, and not so much the last 1% of measurement quality of that one sensor. And algorithms and software are as important as the actual measurement. Starting from the way the measurements are taken, you see that over the years, of course, measuring instruments evolve. They become more complex, they integrate new technologies, but based on digital technologies, on software, we see a very steep increase of complexity because sensors and measuring instruments are combined with some kind of intelligence. That can be something very basic, like you have a measurement and for the sensor, you want to avoid certain unwanted behavior like a temperature dependency or a reaction to vibration in the environment. So you come up with a software to compensate for these unwanted effects by ways of processing. So far, so good. But as soon as you take the instrument and put it in an existing traditional calibration environment, you may see very strange behavior because maybe the software engineer wasn't aware of the way you do the calibration. You as a metrologist don't have access to the actual raw data, but only to the process data. And then you may end up with a situation of a very, very complex measuring instrument, which calls itself a smart sensor, but seems to be very dumb in the sense that it behaves very strangely. So there's an increasing complexity because the software adds to the complex already existing and evolving complexity of the instrument itself. This complexity even increases if we then go to these distributed measuring infrastructures and sensor networks, because then they are combined with other sensors. So you have all these different sensors of maybe same or different quantities. They are combined in the so-called edge. So you may have a computer in place that does some kind of processing to fuse the data, derive information, and provide that to the next level in the measurement infrastructure hierarchy. If you want to do a quality assessment of this, or if you want to do a metrology assessment of this, then you have a very high complexity, a very complex situation here. Let's say you take again the example of an autonomous vehicle. If you want to decide if that vehicle is capable of working properly in a given environment, you have to take the whole set of sensors and the data analysis the system into account, and you have to have a systems assessment rather than an individual measuring instrument or software assessment. Again, here you can have more efficient work with such systems when you have machine-readable metadata in place, like when you know from the metadata about the sensors in the network, what are their measured quantity, what is the uncertainty, is the data quality and data provenance, and so on. And again, also, if you have this higher level of machine understandability, you can have a higher level of automation in such systems, for instance, based on a ontology, which is one way of representing information in a machine readable and even machine actionable way, that a software can understand and relate information from different sources. Then you have not only the measuring instruments, but also the software that you need to take into account. And more, we earlier talked about very briefly about artificial intelligence, more and more you have so-called intelligent software in place that does machine learning or other data-driven analysis. And it's usually the same kind of workflow for the analysis of the data. It starts with the sensor data. You have some data curation in place, and you have the pre-processed or the curated sensor data. You do some further pre-processing, maybe to compress the data. Then you may have some feature extraction to further compress the data or to select certain properties you want to have from the data. And then you have the actual machine learning based on a neural network and AI or some other maybe more traditional ways of doing machine learning. And here's just one example of an actual system in place to do quality assessment of a product in industry, where they have a machine learning set up in place to assess the remaining lifetime of a product to make sure that maintenance or replacement of the product is done before it breaks. This is very similar to what you may see in the future in other areas of the quality infrastructure, like the machine learning or the data-driven approach to assess the conformity of a product based on measurement data. In order to bring quality infrastructure into this kind of system, you need to be able to understand the quality of the different steps. And if you wanna have uncertainty evaluation in place as a way to assess the quality of the decisions being taken of the evaluation, you need to have the uncertainty translated from the first step of the data to the actual evaluation in the end. And that brings us to the question, how do you do quality assessment? How do you bring quality infrastructure to artificial intelligence? There are some early developments on this. Here's one example from the national standardization, but also on an international level. ISO IEC are working on similar approaches to identify what is the quality of an AI system and how do you assess this. And it always comes back to basically the same questions. How do you avoid adversarial attacks? So how do you avoid the misuse of a system? How do you avoid data bias? So an improper or wrong training of the system. How you handle the data management for the training and testing, and how do you make sure and also assess the robustness of the system. So when we want to develop quality infrastructure for AI, we need to be able to understand and maybe also answer these questions, but also the other way around. When we want to use AI in the quality infrastructure, we also need to be able to understand and answer these questions, because of course, you want to avoid that an AI system in the quality infrastructure can be attacked. You want to avoid a situation where the training data was biased and thereby comes to wrong decisions. and we want to make sure that it's robust and that we have a proper data handling in place. But there's more than AI when you talk about confidence in data and algorithms, and that is simulations and other ways of designing so-called digital twins of a measurement. There are examples already in place in metrology where a physical measurement is combined with what you may call a virtual measurement to come up with the actual measurement result. Here's one example of a product that is already on the market. So you can buy this product. It's used to measure spheres. So like you have in smartphones, the lenses in smartphones, or other optical systems where you have very small elements, and they use spheres to have a higher quality. And what is done here is you have an actual physical setup that creates you this interference pattern. So you see here on the left-hand side, and then you have a virtual measurement in place that is basically a digital twin of that same physical setup. And then you change that in the way that you change the virtual surface under test until the virtual measurement and the virtual pattern looks identical or as close as possible to the actual physical one. So you bring both together, and only with that then you end up with a measurement result for your surface under test. So in this case, without the virtual measurement, there is no measurement result. So if you want to have a quality assessment of this, like a calibration or any other kind of assessment of the quality of the system, you need to be able to also have a quality assessment of the virtual part of it, calibration of it, for instance. Similarly, in the area of flow, when you want to have a digital twin as a way to do predictive maintenance, for instance, for a flow measuring device in place, then you need to understand the quality of the simulation of the digital or the virtual part of it in place to really be able to understand and assess the quality of the virtual part of the quality assurance. Of course, this can also be used to do product design, like in this example here. It was analyzed how non-ideal conditions in the piping. So if you have an elbow very close to the measuring instrument, this causes turbulences. How does this affect the instrument? So this is also a way how virtual measurements and thereby algorithms help in the quality assurance. So you see, there are so many elements and aspects to digital transformation, and so many areas where the bodies of the quality infrastructure need to work together. So this joint statement of intent signed last year, and there are still organizations joining in, is very important. It's just the beginning of a longer journey of collaboration. To sum up that first part, digitization is a process going from paper to digital. Digitalization is a process for having this digital in a structural way, structured data to allow automation, which also needs structural changes in the way we work with the data and create the documents that are now printed out as paper documents. Digital transformation is then the consequence of taken opportunities that arise from a successful digitalization and from in some areas, further structuring and more granular structuring of documents. And it's also obvious that irrespective of whether the quality infrastructure bodies embrace digitalization or not, it is taking place. Companies are doing it. Companies are digitally transforming their services and products. So the quality infrastructure is already challenged in various ways and is requested and expected to take the opportunities that are there and we need to leverage opportunities by carrying out collaboration across the scientific and quality infrastructure. And before we now go into the second part, because the first part was already quite long, I would like to ask if there are already questions to that first part of my presentation.
พี่ฟลอร์มีคำถามอะไรไหมคะในส่วนของพาร์ทที่1 I think they have no question now. Maybe you can continue in the second part.
Okay, great. Now, in the second part, I want to look closer into how do I get started. So if I realize, okay, this digital transformation, it's something I need to care about. I have now a rough understanding of what it means. I've seen the many examples of the challenges that are ahead of me in the digital transformation, but how do I start? What are the next steps that I could take? And I always encourage to start where you are right now. So if you are a body in the quality infrastructure, consider to take a step back and look, where am I in this interplay of the elements of the quality infrastructure? Like as a National Metrology Institute, like PTB, we are connected to several elements of the quality infrastructure. And the quality infrastructure is the backbone, is very important, and its backbone are accreditation and traceability to the SI units. So for Metrology Institute, this traceability and accreditation is a starting point to look more closer into, okay, what are the processes that are needed there? What are the documents being shared, and what are the information being shared and worked on that I need to have a closer look at how they will look in the digital world. Standardization is another example, in particular important for smaller and for smaller economies, for SMEs. And it's also a way to protect certain properties. So when you talk about digitalization and digital products from a perspective of a quality infrastructure, it's also worthwhile looking at, okay, what are the things that I want to protect against? And do I need to have standards written to make sure that those requirements are met? So it can be regulation on a political level, on the regulatory level, but it can also be part of standardization, like in the area of AI. This robustness, explainability, transparency, avoidance of data bias, and so on. If you put all of these into standards, you can then say, okay, for a conformity assessment, an AI product has to comply to these standards. So that's important also for consideration of where to start. Then you can look at what are the products and businesses that are most relevant for me as an organization. What are my biggest stakeholders and customers that may also be most likely to collaborate with me to jointly address the pressure on the QI based on the requirements towards the QI to transform itself and to be able to address digital products. There may also be new things you have to establish, like in metrology, there are new measurements that arise from the use of digital products, like in high frequency communications. You not only have the actual physical properties in place, but also things like digital error based on the quality properties of the communication, or the simulations and virtual measurements I just presented also requires new or also lead to new ways you have to do metrology in order to make sure that you can integrate these in a quality infrastructure. So to sum that up, start from where you are, look into how are you connected to your stakeholders and to the other elements of the quality infrastructure in particular. What are the most important and highest impact elements that you want to focus on, and what are potentially new fields you have to establish and create in your organization. One closer look in legal metrology, because there the highest level of regulation is in place. It's also the field where the quality infrastructure has the highest pressure to do something, because there, if things change, they have the highest impact. So if you have a more efficient quality infrastructure in that area, it has the highest impact on a more efficient business for the companies and a more efficient put in place of regulations and regulation enforcement, in fact, even. Development of national standards and also digital references is one thing that needs to be taken into consideration if you want to digitally transform these processes in the product lifetime in the quality infrastructure. This is from the perspective, of course, from a metrology institute. So looking into how our measurements taken place and being stored and communicated, data and algorithm taken care of, and so on. And then, of course, and like mentioned earlier, these arrows here are the communication of information from one body or from one organization to another one. And in order to have this digitally transformed, you need to consider, how do I provide information? How is the next element in the process working with that information, and what are the systems that are in place on both sides, and how can we exchange data information beyond sending email between each other or putting data document files on some kind of a server. So installing some kind of a cloud server somewhere and storing data there is not helpful at all. Here's one example from the regional metrology organization Euramet. When they started working on the digital strategy, they looked into what are the fields, what are the areas that we understand to belong to digitalization. And they identified the metrological services and their digital transformation as one of the major parts they have to consider. Also, mathematics and confidence in data, adopting open science for metrology, and connectivity and data quality in distributed systems. So what they did is they put everything on the table that everybody in the room or involved in the strategy development considered as an element of digitalization, and then started clustering all of these different pieces as a starting point to then say, okay, what is needed? What are the steps that we need to do for a digital transformation of metrological services? What is needed to adopt open science for metrology, and so on? So that's the starting point. Start with putting everything on the table, cluster it, and then start with the cluster headlines. And this is what Euramet came up with as their mission statement as part of the digital strategy: to foster the uptake of digital tools, oversee and guide the digital transformation of metrology together with industry, and engage with external parties, again, collaboration. The overall aim of the Euramet digital strategy is to take the lead in the digital transformation of the European quality infrastructure, not so much because Euramet thinks they can do it best, but they realize that they need to bring what they learned is needed for metrology to the other bodies of the quality infrastructure to collaborate on a joint approach towards digital transformation. And then, of course, you have to consider, how do I implement this? Now, if you have identified the steps that are needed, you need to have some way of implementing this. And one approach that you can see now in various regional metrology organizations, but also in other areas, is the creation of dedicated groups to guide, steer, and communicate the digitalization steps to the implementation of the digital strategy. APMP has a digitalization focus group, the DX focus group. In the Americas, SIM, the Regional Metrology Organization, they also have a digital transformation working group. At the RLMO roundtable, so in legal metrology, digital transformation is always a topic of the agenda of the roundtables, and so on. So there are certain groups and elements that always have this on the agenda. And this is important because otherwise you have the strategy, you publish it maybe somewhere, or you circulate it in some way, and then nothing happens because nobody feels responsible, because the topic is so huge that everybody could do it. And if everybody could do it, nobody will do it, because everybody will wait for the others to start something, to then learn from that and take it, and let's see what the others do. And then when everybody does this, then nobody will do anything. So you need to have a certain group, of course, with a mandate and with a mission statement of what to do. And then you need to make sure that this group is connected to the other elements, like in the example of Euramet. The working group on digital transformation is closely collaborating with the technical committees and with the metrology networks, so the other bodies of Euramet. And similarly also for OIML, the digitalization task group is collaborating with the project groups, is collaborating with the OML certification system and the OML SEAM, so the group for the emerging economy systems and metrology systems. So you need to connect this group in order to avoid that it is this strange group of nerds talking about digital stuff that nobody understands, and we have no idea what they are doing, and they have no idea how to bring their ideas into the actual organization and structure. Then, of course, you have to look at your own internal processes. Here's an example of a laboratory. So you already have certain ways you do in a laboratory measurements. You take the measurements, you do the analysis, and then you put together a report to hand it to your customer. And you have to identify what are the ways in which I gather and work with that information and data. And then, of course, the first step need to be the digitization. So to make sure that you have no longer paper-based processes in that work. So you have to have digital documents in place. That's a very first step, of course. But when you are at that step, you could also make sure to do this in a proper way. Like, as I said earlier, even a Word document offers the possibility to define field elements with names that a software developer can use to write a software to automatically fill these elements in the Word document based on another data source. Even more, if you want to create an XML document, you could use similarly a software that creates the structural elements of that software. In the end, you can still make a PDF document out of it, put an electronic signature on it, and send it to your customer. So even in that step of the digitization, you could make the processes more efficient and make it ready for the next steps. And this is what I mentioned earlier with this interoperable process that we're working on at PTB. And similar, that holds for all other areas in the quality infrastructure where you have a process in place that starts with information coming from one source, you process that information, and you provide something to your customer. And often you'll realize, well, that's quite complicated. And when you look at it, why it's complicated, you often realize, well, it's that complicated because the analog process is too complex for digitalization. And often people don't know the analog process. So the first thing that we start at PDB when we digitalize or support digitalization of a laboratory, for instance, for calibration, we talk to them. Okay, what is a process? Let's say there is the request from the customers coming in. What are the steps that you do to process that request from the customer? And then you realize there are certain complicated steps in there. And if you would try to digitalize them right away, it would be a very bad digital process. So first thing you should do is to harmonize the process or to streamline and make more efficient the processes of working. And one way to approach this is to consider the process from the end. So if the outcome of the process is a digital certificate, okay, what is the data that I need to put in that certificate? And how can I make sure that this data is gathered and processed in the most efficient way? And that then defines the process that you need to have in place to make sure that you have an efficient digitalization of the process in the lab. For instance, in a digital calibration certificate, you have administrative data like what is the customer, what is the product, what is the name of the lab, what is the date of the calibration, and so on. Then you have the actual metrological data that needs to go into the certificate, like the measurement results, the data analysis outcomes, and so on. And then you may have some processual data that is not needed for a certificate, but for the internal quality management, like who did the calibration, um, who approved the calibration certificate, and so on. So all the information in the background that is needed in your system later on to provide an audit trail in case you are audited for the calibration. And if you do this, so if you have the proper connection of the different steps of a measurement and you have them in the digital way, you can have more efficient ways of working in the lab. So you can leverage the efficiency of the way you work and can improve your way of working and become more efficient. So until here, there's no need for your stakeholder, your customer, to be already able to work with that. Of course, they should be able to work with a digital certificate when you give it to them, when you send it to them. But you already yourself can benefit from the digitalization because you end up with more efficient processes. One way of approaching this beyond this, making interfaces between systems, is to make sure that the data you acquire and provide internally and make use of adheres to the so-called FAIR principles. That's a set of principles originating from the scientific community to make data, measurement data in that case, or research data, findable by others, accessible by others, interoperable with each other, and reusable in the sense that you can reuse the data in other areas or in other circumstances. If you look at these principles more closely, there are two things to realize. One is, well, that there are some core methodological competences that underpin the FAIR principles, like the traceability to the international system of units is a proper way to make data accessible, interoperable, and reusable. But more importantly here today is that realize that if you adhere internally also to the FAIR principles, that's a very important step to ensure a more easy and efficient interconnection of different systems. If all of the data sources in the organization adhere to the FAIR principles, it's very easy to write a software that combines and exchanges information between those. And it's more easy to come up with digital systems for a more efficient internal way of working. And that means that, or it may mean that you have to get rid of tools that you use today. There are, even also at PTB, there are laboratories that use tools like OneNote or even paper-based documents for their notes in the laboratory as a lab notebook. Many use Microsoft Excel for the for documenting and analyzing data. Or they use some kind of a file storage where they put the files in a folder structure and have this as a way of documenting. All of these don't embrace the FAIR principles and adhere to the FAIR principles. An Excel document is unstructured. So if you change the way you use the cells in the Excel file, the software that formerly used and extracted the data breaks down because the information is no longer in the field the software expected it to be. If you make data and algorithms available between labs, groups, and disciplines based on the FAIR principles, then you already have carried out a very important first step of making the processes, the internal processes, more transparent and more efficient using digital technologies. Sometimes it's difficult to start with the systems you have in place for a productive use because the calibration lab, for instance, it needs to run calibration all the time because there are so many customer requests to work on. The conformity assessment body, they have a lack of personnel to change a setup, an existing setup, to try out new stuff. So one way of still getting started is to define some kind of demonstrator pilot project, to say that, okay, here is a project where we could try out stuff like in a test field and use it to build competence, but also use it to demonstrate, look, what we've came up with, it actually works. One way that we quite recently started approaching this is with this a pilot project shown here. It's basically a combination of different information and data sources to try out and test the interoperability of systems based on persistent identifiers and machine readability. The core is that one here at the bottom. Ignore the formula. It makes no sense, I know, but it's a nice formula. Everybody knows it, and it is a good way of demonstrating what we want to do here. You could start with saying, I want to calculate the energy, but I don't know how, and I want to receive information from a set of standards that gives me the information automatically in a machine-readable way. How can I calculate this? So you use this to program an interface to a standardization database that gives you then from a smart standard the formula back. Here's the formula that you have to put in place. So first step of machine readability. Then the value for mass. How do I get this? Well, in this case, we use a set of calibration certificates that we use from as a way, as a container for information from a key comparison. So several results, then all being fused together, summarized to come up with a common reference value for the mass and its uncertainty. And we use that to demonstrate first of all, how you could structure in a machine-readable way key comparison information, but also how to work with information that comes from such a certificate from a DCC to extract information and work with it in another system and implement it there. The constant for the speed of light can be taken from a constants database, again using persistent identifiers and machine readability. So to do this in an automatic way, and there we evaluate the communication and interoperability with those kind of databases. From all of this, then you could create a kind of a digital report. Could be a measurement report, a test report, a key comparison report, and in case it is a key comparison report, maybe you want to have some kind of a digital signature or seal attached to it, converted to in a proper format for the database you want to provide it with, and provided for. And one example that we look into at the first step is to how to put this in a key comparison database that already has a given structure. So it's not important the individual elements here. Important is it's one pilot project where we can test out several tools and technologies, collaborate with others. So we have approached the standardization body to work with them on the implementation of standards. We work with the CODATA database formats and so on. So combining different pieces together without harming any lab. So we don't have to interrupt any lab, but still can communicate and test out new developments. And then, of course, if you have started these projects to digitally transform the way you work, these interfaces between platforms, the step from paper-based processes to digital documents and maybe even more to structured documents, you may look into what are novel services that I can provide based on the now available digital products and now available digital certificates, standards, or whatever. The digital services in the quality infrastructure need to serve as an anchor of trust in other digital infrastructures. Of course, digital product passport is just one example of that. Customers and stakeholders need to be able to progress in their digitalization based on the services and products that you provide. And of course, it's to be expected or even requested by stakeholders that the quality infrastructure bodies look into new technologies to improve the way the quality infrastructure works and becomes more efficient. And at the last point of my presentation, I want to go into one particular service that is often requested, and that is that of remote services. Can't we do everything remotely like we do now? This hybrid workshop with you, can't we do remote verification or remote calibration? And to answer the question of can we do remote calibration, you have to look into what a calibration actually is and what it means. And there are two basic sources of information. One is the International Vocabulary of Metrology that defines very clearly what a calibration is, and the other is the ISO 17025, the standard that defines what a calibration laboratory has to do to be considered a proper calibration lab that can be accredited. Now, the VIM says for a calibration, you have to have a measurement standard that is a reference for the measurement. So if you want to do remote calibration of any kind, you have to find a way to provide a measurement standard remotely. There are examples where you can build it in, like there are temperature sensors that have a built-in reference with a known melting point, for instance, that you can use then to recalibrate the sensor. In other areas, it may be much more complicated, like for a weighing instrument, for instance. How do you derive a remote measurement standard? So if you want to provide services for remote calibration, you need to have a definition of what is the measurement standard for that service and how do I make this remotely accessible. And second, the ISO 17025 asks for several competences and responsibilities of a calibration laboratory. So if you do remote calibration, you also have to take these into account. And the first is there that that the laboratory is responsible for the management of all information. So when a laboratory offers remote calibration, the laboratory is responsible for the remote management of all information that is in place. So it's not sufficient to just put a webcam somewhere and then let somebody else do the work, or in whatever any other way work with remote access to the infrastructure without having access and being able to assess the quality and trustworthiness of that. So if you have a remote calibration service, it's not sufficient to just have access to the data source of your customers. The laboratory is should also specify responsibility, authority, and interrelationship of the personnel carrying out the calibration. So if you do remote calibration, that may mean you have a software in place that does some of the parts, and you have to have responsibility, authority, and interrelationship of their software, because it's then kind of personnel you have to manage. Or you have people from the customer in place that have to do certain steps, and you're also, as a lab, responsible for them, including, and that the third point I want to mention here from the ISO 7025, the lab shall ensure that the personnel have the competence to carry out the calibration. So if you want to have a remote calibration service, you have to assess the competence of the software that is in place, if there is any software, or you as a lab are responsible for the competence of the people at your customer's place that help you with the parts of remote calibration that you can't do, like putting the right weight in place and so on. So you as a lab are responsible for the data that is used, for the responsibility and authority of the people in place and the software in use, and of the competence of the people in place and the software in use. So a remote calibration, it's possible, but I think it's very complicated. And I would say in most cases, it's much more easy to not do a remote calibration, but do a calibration in a traditional sense, of course, made more efficient using digital technologies. And that brings me to the end. What are the things that we need to consider? We need to consider that digital communication of data information will become the standard, not only in meteorological services, but across the whole quality infrastructure. Distributed measuring systems and sensor networks become more important than the individual sensors that holds for all areas of the quality infrastructure. As again, not only for metrology, so distributed systems and distributed quality infrastructure management. And algorithms and software are as important as the actual measurement, talking of virtual measurements, of digital twins, and of artificial intelligence, of course. Thank you very much, and I'm open for questions.